Let's talk after class. So let's think about the coffee drop problem. So what do you expect to happen? So we saw basically all of the junk forms in the ring. I think this is true for also when you stain fabrics.
You can't really see the particles moving, right?
Oh, you can. Yeah, okay, good point. Okay, so we saw this. And if you zoom in a little closer, you can see what's actually happening. So here you have particles suspended in the flow, and you can see the surface flow is marked by particles being swept towards the edge of the. Okay, so these are particles are suspended throughout the fluid, and you see basically things are being pulled over towards the edge, and it's the things at the surface which are being pulled towards the edge.
Yeah, that I could imagine. Then why are these guys being pulled?
Okay, so that's what we have to figure out.
So it's coffee powder, right?
Yeah, because coffee is basically it's water with all sorts of junk in it, oils and so forth, right? Okay, so we have
One quick question, which is really not a joke. Can you tell the wine age by its tears and stuff like that?
so yeah, so the real experts, enologists, as they're known, they can measure. It's one measure of the quality of a sherry, for example. So in Spain, in Jerez, they have they will basically look at the spacing of the wine tiers and the size of the wine. That's going to depend on both the alcohol concentration and the sugar concentration. So the sugar influences the viscosity, and so to get the right balance, they know exactly if you drink enough of the stuff. If you've had enough wines, you'll know what the tiers should look like. So that is a serious measure. It's a good question, and there are people who are really. I'd actually love to talk with someone from that neighborhood to see what they know and how they measure things. It'd be interesting because you could basically rationalize all the different forms. Right? There are lots of questions, like even just the instability of the tier line. Right? You basically have fluid being pumped up in a thin film, accumulating in this tier line, and then that's going unstable, and so that's basically like a Rayleigh plateau instability, which is what we're going to do in class next time, but it's slightly different. It's sort of half a cylinder, and it's depends on viscosity as well. Okay, so this is our coffee drop, and we've just seen that what happens is junk is being swept towards the edge, and we want to try and understand why. So this is my understanding, is that we have this hot drop, which is losing heat through evaporation. Okay, so it's losing heat. Where is this going to have the most impact on the temperature? Right. So I would suspect here, you have this amount of surface area and only this little amount of volume, right? Compared to here, you have this amount of surface area and this huge amount of volume. So basically, near the corners, you're really going to be pulling heat out and cooling it. Okay? So you get cold fluid here. This is the same argument they use for the tiers of wine. You, again, in the thin layer, in thin layers, you have a relatively large surface area to volume ratio, right? So you basically, things get cold here, which means high surface tension here, and as a result, you have Marangoni stresses, which basically pull everything in. So you basically get a large overturning circulation, which looks like this, and will tend to cause junk stuck at the surface to develop in piles. So at the end, you basically have a ring and all of the junk is stuck in this frame.
Video, we are not seeing one rolling off, particles going over the other. It's really 3D, right?
Yeah, this is, yeah. I think some of these particles are on the surface and some of them are in the bulk. So the ones that are moving are the ones on the surface.
So this from above, right?
Yeah. Yeah, so that's the line there. But you can see they're going and sticking, right? They're going there to die.
Yeah, that's why I was wondering. I mean, won't they just come back when the go down?
No, they're stuck on the surface. Right? So they're basically surface active. So they get stuck on the surface. Which brings us to our next subject.
We can only see that in small drops, right?
You cannot? What's that?
You can only see that in small drops.
I don't know. I can't see it at all. I mean, these are. Oh wait! I'm starting to. By the end of class, we'll see it. Yeah, it's working. It's working. Yeah.
So, before we jump to
Mhm.
the subject, you said you could tell whether it was Marangoni or Ray Method according to the.
Yeah. Up. You get downwellings in the center for Rayleigh-Bernard. Sorry. Opposite. You get downwellings above peaks in Marangoni convection. It looks like this, and it's the opposite for Rayleigh-Bernard.
How about the case of the hexagons?
So the hexagons, it's true here. The same is true here. So the hexagons they'll typically have either a trough or a peak on the surface, depending on whether it's. Sorry. Wait. So let's look at that video. I'm trying to remember where the peaks are here. So this is coming up at the surface. Yeah, I need to see. You need to see what the surface elevation is, but that's always true. Okay. So now we get onto surfactants. Okay, so I have notes. You have notes on this, so you don't need to follow. I'm going to try and go mostly from these slides. Okay, so surfactants, like some of the junk you have in coffee, and certainly soap, these are molecules that want to be at the surface. And this is typically because, so for an air-water surface, they'll have a hydrophilic head and a hydrophobic tail. Okay? So they basically want to be in this arrangement. This arrangement brings down the net energy of the system. Okay? And so the actual surface tension depends on the so if we have a fluid with a bunch of these surfactant molecules in it, say soap molecules, the surface tension depends on the concentration of the molecules in the bulk. Okay? And it turns out it's kind of nice in that there's a linear dependence. So basically, as we increase the soap concentration, the surface tension goes down linearly until we reach this critical value. And this critical value, which is called the critical micelle concentration, there's no further dependence. So basically, the system becomes saturated. If you increase the surfactant concentration high enough, the surface tension no longer reacts. And the reason for this is above this critical concentration, these structures form. Okay? And when these structures form, these so-called micelles, there's no longer an advantage to the molecules being at the surface. If these things go to the surface, they can exchange, they're just as happy to be in these groups as these. Okay, okay, and so But this is, so assuming that we're below this critical Misos concentration, so it's kind of interesting. It's saying that the surface tension will change up to a certain concentration if the fluid is in some way contaminated with these surfactants. And a lot of biological materials are surfactants. But if you get a sufficiently contaminated surface, then there's no longer gradient, so you no longer expect Marangoni flows. But if you're below this critical Misos concentration, then generally the surface tension depends on the concentration. This is, so I'm using gamma to denote the concentration at the surface and C to denote the concentration in the bulk. Okay? And so if we're below this critical concentration, then we can have gradients in surface tension, and these can induce Marangoni flows. So we've seen already at this, discussed this soap boat. So it's a piece of wood with a piece of soap at the end which leaks out, decreases the surface tension, and so gives rise to a propulsive force which drives the boat forward. Okay? Okay, so what about these surfactants? So how do we characterize them, and how can we describe surfactant-laden interfaces analytically? So first off, what are their properties? So we've seen that they can exist in the bulk or also in the at the interface. They can some surfactants can also sublimate, that is to say they can pass into the gaseous phase. And so the rate at which these things diffuse along the surface is prescribed by the surface diffusivity. There's also the solubility, so that's the ease with which they pass from the bulk to the interface. If one ever hopes to make any analytical headway, you hope to be dealing with insoluble surfactants, which is to say that they're just stuck at the interface, so they can't change from one phase to the other. Okay? And then there's the volatility, which prescribes the ease with which these molecules pass from the interface into the gaseous phase. And again, if you have a situation where that happens, you're pretty much lost in terms of developing analytical models. Okay? But so this is the equation. So again, as is generally true for Marangoni flows, we have now this new phase. So either we saw temperature, concentration for alcoholic flows, and now we have the concentration of surfactants. So in addition to Navier-Stokes and the boundary conditions, we have to keep track of the surfactant concentration within the on the surface, and typically that depends unless these guys are non-zero, it also depends on the flow within the bulk. Okay, so this is the equation for the evolution of surfactant within along the surface. And so we can see basically surfactant can be advected. So this is just our advective flow. So it's basically moved by the surface flow. Okay? So these surfactants are moved around by the flow on the surface. And then we have the surface expansion term, which I'll elucidate. This is basically if you have a bubble and it's expanding, so the surfactant is on the surface, then as it expands, the local surface area is going to increase, right? And so the surfactant concentration is going to decrease, right? So this has to do with the fact that this is again for motions with non-zero surface divergence, right? So if there's a surface divergence, then there will be a change in the concentration. And then we have these terms here. So this J involves, has the solubility, depends on the solubility, so the extent to which the surfactant can pass into the bulk or vanish off the surface through sublimation. And then we have the surface diffusivity. Okay, so it turns out that in a lot of situations, if you have an insoluble surfactant, so the surfactant is just stuck to the surface, this is zero, and oftentimes the surface diffusivity is very small. So then you're just dealing with this equation. So this is just saying that the surfactant concentration is changing in response to the flow on the surface and the change of the geometry of the surface, and so you can actually make some headway. So I just want to highlight this term.
So the surface diffusivity is usually for surfactant?
Small.
Small?
Yeah.
So that means if you put a drop of surfactant
Yeah.
on the surface, it won't diffuse
it won't diffuse much. Basically, the flow resulting from you'll get a Marangoni stress which will dominate it, right? So basically the convection will always dominate the diffusion. But again, typically you can say, if you're trying to actually solve a problem with surfactants, if it's insoluble, you throw this away, and then diffusivity is small, you throw this away, and then you're just dealing with these terms. Okay? So let me just solve, to highlight the role of this surface expansion term, we'll solve a little problem here. So if you look at the expansion of a spherical bubble, so you can ask how the surfactant concentration is going to evolve with the bubble radius if it's just expanding. Okay, so here's our bubble. And the local velocity field is just dr dt. So if we look at this, if we assume that there's no surface motion apart from the expansion, then we can write. So the local rate of change of surfactants. So we basically just keep the first and the third terms there. Gamma div surface n dr, so n. So the divergence of the normal for a sphere we've seen before is just 2 over r, and we know ur is dr dt. So we get so we have this, which we can solve. So we get the concentration goes down like 1 over r squared, which is of course what we expect. In particular, we expect gamma total times 4 pi r squared to be constant. And that's just a statement of conservation of surfactant, right? So if we start with a certain concentration, it's just going to decrease like 1 over r squared as this thing expands. So that's saying there's the conservation of insoluble surfactant, right? Okay. Okay, so the next slide is one of the most important ones in the course. So if you're going to understand Marangoni flows, you have to understand this slide. Okay, so we know that the presence of surface tension imparts to the surface an ability to resist curvature. So we know it's energetically costly to deform a planar interface. A planar interface has the minimum area. But there's nothing resisting surface divergence if you have a clean interface, right? Right? If you have a clean interface, you have a jet coming up and causing there to be surface divergence. That's not changing the surface energy at all, right? So the system doesn't care. But if there's surfactants present, then they do care. And any motion with non-zero surface divergence is going to be resisted by the presence of surfactants. Okay? So imagine we have these little dots represent surfactant molecules. And so imagine we have a flow with non-zero surface divergence. So imagine, so this is the surface of your swimming pool, and we have a jet coming up. The jet is hitting and it's basically spreading, causing the interface to spread like that. Okay? So if we do that, as this, if we follow, say, a ring of fluid, it's basically going like this. So we have non-zero surface divergence, which means that because of the presence of the surfactant concentration is decreasing here, right? So it's basically going, we're taking a little circle of fluid and it's expanding radially. So we're decreasing the surfactant concentration inside, which means that you're increasing the surface tension, right? If you're increasing the surface tension here relative to here, then there's going to be a Marangoni stress which resists this expansion, right? So as a result of this non-zero surface divergence, you're generating a Marangoni stress which is then resisting the motion, right? So it's going to get killed, right? So you're basically preventing surface motion with non-zero surface divergence. So similarly here, if we have a motion characterized by surface convergence, then if we have surface convergence, again, if it's a clean surface, there's nothing at all resisting it because the surface energy is not changing. But now, because of the presence of surfactant, you're basically concentrating, so you can have high surfactant near the point of convergence, which means low surface tension, so this is again going to be resisted. Okay? So the surfactant acts always to resist motions with non-zero surface divergence, whether it's positive or negative. Okay? And so this interface then behaves like an elastic, right? So we know if you have a balloon, there's a resistance to expanding the balloon, compressing the balloon, right? It wants to keep the tension uniform everywhere. Okay, so crudely speaking, we can think of a clean interface as being a slippery trampoline. So basically, we know that by deforming it, you can generate normal forces, but you can't generate any tangential stresses. But when you have Marangoni, if you have surfactant present, then you can generate Marangoni stresses which are tangential. Okay? So you can think of this as being more like a trampoline. So there's an effective elasticity of the interface imparted by virtue of the surfactants. Okay, so is that a clear picture? So again, this idea of, so we talk about Marangoni elasticity. So it's this elasticity which stabilizes soap films, as we'll see in a moment, and gives rise to all sorts. It also is that which resists the generation of waves on an interface. So do you understand that? So Marangoni elasticity is the catchphrase here. Okay, yeah?
Yes, I think it's a silly question, but why is surfactant...
There are no silly questions, except for maybe this one.
Okay. Why does it always decrease surface tension?
Okay?
Why is there like any substance that would like be a surfactant that would increase?
Oh, so yeah, there actually aren't any as far as I know. It is a question of, so you have a clean interface. In some sense, you're bringing down the surface energy by adding the surfactant, right? Basically, you're taking this thing and it wants to be at the interface. So we know that things at the interface don't want to be there. That's the origin of surface tension, right? The fact that these fluid molecules don't want to be at the interface because it's energetically unfavorable, right? So you're replacing that by a molecule that actually really does want to be at the interface. So in some sense, you're bringing the system energy down, so you're bringing the surface energy down. See what I mean?
You bring this energy down?
Because you're replacing a molecule that really doesn't want to be at the interface by a molecule that really does want to be at the interface.
So why does the energy bring, if I understand that the energy goes down and there's the rest, so why does the energy go down with that? With the molecule that wants to be there?
Because the surface energy is simply a measure, surface tension is a measure of how much the surface molecules want to be there. If they really don't want to be there, the surface tension is going to be very high. And if they do want to be there, then it's going to be very low. So it's a question of...
As the cost goes down, the
Yeah, surface tension goes down, yeah.
Okay, got it. Thanks.
Yep. Yeah, we'll see that in a second. Okay, so we've seen this Marangoni propulsion many times, so we know that if you have a floating object which has different, through chemical means changes the surface tension on either side, then there will be a net force. We get that by integrating. I think that's on your problem set, or maybe not. But we've seen it several times, and here we see, so this is, I don't think you've seen this one. So these are releasing a volatile surfactant. So with soap, they run out of gas, right? Because they eventually coat the entire surface, and so there are no gradients in surface tension, but these are releasing camphor, which basically hits the surface and then evaporates. And so...
You could sell that to Fisher and Price and other kids.
Yeah, so...
There's one that passes the other degree.
Yeah, exactly. So tell me, which one weighs more? Which one weighs more?
Weighs more?
How do you change the... No, how do you change the speed of one of these boats?
Do you use a surfactant?
No, it's the same surfactant. But the drag, right? Because all you can control is the drag. And so the drag is going to depend on where they sit in the fluid, right? So if you want to make it go faster, you want it to sit higher up in the... Because it gets the same propulsive force, but has less drag.
I was thinking that the one behind gets less dynamical pressure from, yeah, like in
The one with
Formula
the
1.
number craft.
Sorry, what was that? Sorry?
The one with the number craft.
Yeah, the blue one's zipping along a little fast. Yeah, so the green one must be sitting deeper in the water. So, and this, I've shown you this one, I know, but this is the same principle. Here you have a volatile surfactant, this being alcohol, which propels the boat around the martini glass. Okay, so let's talk a little about soap film. So this is another sort of canonical example. So what's the force balance? So, well, before we look at the force balance, let's look at what stabilizes a soap film. So we all know that soap films are very stable, but water films are not, right? Try blowing a bubble with a water film. Okay, so how is it that we can rationalize this stability of soap films? Well, soap film is simply a water film, but the water film is covered with soap, so it's a surfactant. So soap film if you look at the stability, basically, so to rupture a soap film, so let's imagine we have a soap film and we try tweaking it. So this is our soap film. Okay, so let's say we try pinching it. If we try pinching it, what do we do? Well, so you're increasing the local area. Right, this area here, in this region here, we've replaced this interface with this interface, right? That interface has larger area than that. So that increases the local area, which means that you decrease the local surfactant concentration. You decrease the local surfactant concentration, you increase the surface tension. You increase the surface tension relative to that out here, and you get a Marangoni stress which fills in this hole. Okay? So you generate a flow which resists the pinching. Okay? So I defy you to try and think of a flow which causes rupture of a soap film which doesn't have non-zero surface divergence. So again, we see that the presence of surfactant is to resist any motion with non-zero surface divergence, and this will serve to stabilize the film. Okay, and so the second issue is the force balance. And we know, again, we know that Marangoni stresses have to come in. If it was a water film, it could not be, the largest length we could get it would be a capillary length, but we know we can get some very tall, stable soap films. But the force balance is basically, if you look at a chunk of fluid here, then what's supporting the weight? Well, we know that the surface tension is going to be, so it turns out there's a gradient in surfactant concentration along the film, and the resulting Marangoni stresses support the weight of the film. Okay? So you have basically low surfactant concentration at the top, which means high surface tension. So the difference in surface tension between there and there is what supports the weight of this film, which can be expressed in this way. Huh?
So the difference in surfactant concentration arises naturally when you form the film.
Yeah. Yeah, so gravity comes into the dynamic. So the force balance is rho GH of Z. So it's kind of interesting, actually. So when you look at a soap film, from the color, you can calculate the thickness. Okay? And so that gives you a proxy for the local surface tension gradient. So you can actually, by looking at it from its color, you can see what the local surface tension gradient is. And so this is something which is, so this is basically chemical, and this is what you can then infer, is a change in the local concentration. Okay, and so that's just talking about the force balance, but that's not talking about dynamics, right? We know, we've all argued many times, that any Marangoni flow has to be dynamic. So this is not a static situation, right? There has to be some flow. So what's the flow looking like? Okay, so basically within the film, you have a flow, basically, which looks something like this. Okay, so on the surface, we know that the Marangoni stress has to be balanced by viscous stresses. Right? We know that that's comes from the most general tangential stress boundary condition. So mu, du, dx, we call this x. U or x. So that's the surface stress boundary condition. And inside, you basically have a balance between gravity and viscous stresses. So again, we know that inside the film, surface tension is gone. Surface tension only appears in the boundary condition. But so you basically solve that inside. So this is Marangoni, viscous stress, balance, and here is balance between gravitational and viscous stresses. Okay, but it's important to realize it's got to be a dynamic situation because there are surface tension gradients, and there have to be surface tension gradients in order for this to be stable and in order for the soap films to be as large as they are. Because if there were no surface tension gradients, the largest static situation you can have is always on the scale of the capillary length. Okay, let's just see what we got here. Okay, this is too much fun to miss. Okay, ready? So I'll just quickly, we'll probably come back at these later in the course, but I'll just, so one effect of surfactants, if you can solve exactly the flow for the flow speed of a drop or a bubble moving in another fluid at low Reynolds number. Turns out that when drops become very small, they move much more slowly than you would anticipate. So, for example, if you had a drop or a bubble, let's say a drop moving in another fluid, you expect in the frame of reference of the drop for the flow to look like this. So you have this internal circulation. Turns out that when you have surfactants around, the rise speed of this drop corresponds to that of a rigid object with the same density difference, okay, which is saying that somehow its interface is becoming rigidified, and this is happening through the presence of surfactants. So as the thing rises, these surfactants, which are basically, and these are always present in water and anything else, they stick to the surface, and if you have this sort of motion, they'll accumulate at the back of the drop. So then you have a gradient in their concentration. The gradient in surfactant concentration gives rise to a surface tension gradient, and that surface tension gradient rigidifies the surface of the drop. So this drop then moves as if its surface is rigid. Okay? And so, and this was a puzzle for many years, and they finally, I think it was Charles Maldarelli came up with a very good idea that if you supersaturate the fluid, because in order to try and test the theoretical predictions, they'd have to use triply distilled water. He said, why don't we use really dirty water? So they just basically saturated the whole system with surfactant, and then you get rid of gradients in surfactant concentration. You get rid of the Marangoni stresses, and so the drop moves as if the interface were clean. Okay? And we've mentioned the suppression of waves by surfactants, and so the reason for this is as follows. Basically, as you generate waves, particularly capillary waves, so small waves, if you have a clean interface, oh, there is? Oh, okay. Oh, my watch is slow. Okay, well, let's pick it up from next time. Was it 3:05?
Yeah.
Oh, my watch is slow, sorry.